Okay, hello everyone. So today it's my pleasure to introduce Dr. Jieyu Zhao to give our seminar talk on building accountable NLP models on the social bias detection and mitigation. So Dr. Jieyu Zhao just graduated a few weeks ago. Yeah, and she was working on this research topic of fairness in NLP. So this is what I think she is unique in her PhD journey, that she's not only working on some problems that people know is important, but she also create and also identify these as important issues of social fairness in NLP problems. And her research work has been very impactful. And for example, 6 of her paper has been cited more than 100 times in the last 4 years. And she also received a lot of awards, including Microsoft Research Fellow, and more recently, the Rising Star in ECS. Yeah, so without further ado, let's welcome Dr. Jieyu Zhao.
Not familiar with Dr. Okay. Oh, give me a second. Okay. Yeah, thanks everyone for coming, and also thank you, Kevin, for the nice introduction. Yeah, and also very thankful to your help during this PhD journey. Yeah, I would say I'm a PhD student advised by Kevin. Yeah. Okay, let's get started. So we know that nowadays AI models or NLP models are very prevalent. They kind of impacting our lives in various ways. For example, we are all familiar with those chatbots or like personal assistant or the recommendation systems trying to recommend you some good stuff you want to buy or something like that. And also during this COVID-19 time, we have many NLP researchers trying to build systems that can help our doctors to do the search or retrieve some medical kind of records regarding to those COVID cases. So with actually with advanced machine learning techniques, NLP models now have really good performance in many kind of applications. And I want to show you one example called Correference Resolution. So Correference Resolution is a very important task in NLP. It's given some text you want to extract all the phrases in the given text referring to the same entity in the real world. For example, given the short bio about Paul Allen here, our model now can identify that all the kind of text under this blue box referring to Paul Allen, and the one that in the pink color refers to the location Seattle. And also like the light blue color refers to Bill Gates. So it seems like now our model can process the text and extract the complicated correlations automatically for us. It's really good. And here I show the performance of the correference task during the past few years. The x-axis here is the time, and the y-axis is the model performance on some benchmark dataset for this task. So we do see like over the first 7 years or something like that, the model performance arises from about 54 to something near 80%. So it's a really great achievement. Another task we can see like NLP is doing a really good job is in the question answering task. So the task is that, okay, given us some text, we ask some questions based on the paragraph, and you need to extract the correct answers based on this given provided text. Now, existing model can even do a better job than human beings, like shown in the first row. So here, the human performance means the inner agreement between human annotators on the benchmark on this benchmark data set. So again, it's like the performance is so amazing. If you outperform humans. So okay, now it seems we can build AI models can do tasks for us and can do the task better than us. I would say like such kind of revolutionary achievement in NLP models happens especially during the last few years, thanks to the rise of our pre-trained models. And for the last few years, every year we have several new models proposed, and they are becoming more and more powerful. We now have entered a very exciting area, like we can tackle many NLP problems that used to be very difficult. And also a lot of attention is having attracted to this direction. But are we really done? So most of the time we train a machine learning or NLP model based on some benchmark data sets. And existing models, like I said, can outperform human beings in some examples I showed previously. But when we adopt these models in real applications, that usually comes a heartbreaking moment. So it keeps scaling the model size is not enough. We are still in the middle age or early age to realize the accountable NLP model goal. So I will show you some failure example of the current NLP system, especially under the social bias context. So by social bias, I mean that the machine learning model makes the predictions systematically predicates in favor or against certain peoples that are considered to be unfair. For example, the people can be related to certain demographic groups, like related to gender or race, etc. The first example I show is still correference, and we will know this task previously. So in the sentence I show here, a model can successfully identify that the president and he is refer to the same person. And if a model is accountable and does not make any gender biased predictions, it should have similar result when we change the pronoun from his to her very easily. Unfortunately, in this paper, we show that the correct link between the president and her breaks. And similarly, the model fails to correlate females with certain occupations, such as a professor, lawyer, or doctors, which in return also will influence the downstream tasks. Okay, to better quantify the bias in this corref task, we build this data set called Vino bias. We use this data set to evaluate bias based on counterfactual methods. Each sentence in this data set will contain 2 occupations and 1 gender pronoun. And the 2 occupations have different inclination to different genders. If the correct link in the sentence follows the social bias, we call it pro-stereotypical, and otherwise it's anti-stereotypical. We can obtain those social bias from some labor statistics. So for example, the first sentence here, we have the correct link between the physician and the he. It belongs to the pro-stereotypical set, and the following one belongs to the anti-stereotypical set. Also similar to the motivated example, if the model doesn't make any biased decisions, it should have similar performance on these 2 sets. So we will use the performance gap between the pro-stereotypical and anti-stereotypical set as the metric to evaluate bias in this correct model. We tested with different types of models. Here, I want to show the result on the deep neural network model, but it's back to 2018. Yeah. Here, so we show like the performance on the pro-stereotypical set is in green and anti-stereotypical set in yellow. So the model has pretty good performance on benchmark data set, but now we show there is a significant bias in our showing in this Vino bias data set. Here I show that there is bias in Correference Resolution task. Other people have found like the social bias in other applications that can impact our life, daily life. So for example, we know there is people show like there is biases in machine translation systems and in some online toxicity detection tasks or in a dialogue system. not only kind of conducting or detecting those biases by us, the problems of biases in AI have been recognized by the whole society. For example, AI systems have been used in the criminal justice, and the researchers have found that there are significant racial biases in such algorithms. And also about other biases in various kind of scenarios. Nowadays, there are funding calls from the government or from big companies to focus on AI fairness. And also, I'm honored to be supported by Microsoft Fellowship to continue the work on NLP fairness. We now also have research groups working specifically on AI ethics, and we have our community have built some workshops or conferences on this direction. But back to a few years ago, when I started my PhD, there are not so many discussions on this topic as it is today. And I'd like to share some of my efforts on this direction. Before I share my work, I want to say that my big goal is to build accountable and trustworthy NLP models that can be accessible to everyone. In fact, as humans, we also have our own bias, but we can go to some like workshops or tutorials to learn new things and change our perceptions. So one thing we want to ask, can we do the same thing for our models? But during my PhD life, I have made some small steps toward this direction by conducting research focusing on NLP fairness. My work ranges from understanding biases in different NLP models from different layers of the NLP models. And it also covers quantification of the biases and also proposing corresponding mitigation method. Okay, before starting discussion the work, we can quickly recall what is an NLP model pipeline look like. So usually we collect the data from the real world, learn the representations from them, and we conduct structured inference based on the representations to get a prediction, and then we evaluate our models based on the predictions. My work touches the biases from the different layers of this pipeline. It addresses two important tasks about bias detection and mitigation. And here's the overview of my work on the NLP fairness. It serves as a pioneer work in NLP fairness direction, and one of my work won the Best Paper Award at EMNLP 2017. Even though now we have about 30 papers accepted at ACL with the keyword like fairness or bias, but back to 2017, there are almost no papers on this direction. Some of my work has been some of my work has been added to the latest version of NLP Bible book by Dandrovsky. And I'm also honored to be invited to join the panel discussion hosted by UN Women to discuss about gender equality and the social response. And all of my research here they serve the same goal to build accountable and trustworthy NLP models. In more details, my research analyzed several things. First is like we analyze the biases in representations. They are very fundamental in NLP models, and most of existing work are trying to learn representations that can boost the performance in downstream tasks. But we are the first few ones to understand the bias in representations and how will the bias influence the downstream tasks. In my work, I also propose new ways to discover the biases in NLP models, which can help to recognize model weakness. Otherwise, we could incorrectly believe our models and without knowing the underlying issues. In a series of my work, I put efforts in discovering a new category of bias, which is the bias amplification. This task is very challenging as we are now dealing with multiple variables at the same time, And we are, in fact, we are able to find good ways to calibrate the model and reduce the bias amplification. Okay, although the bias detection and mitigation are innovative directions in NLP, but they are actually aligned with existing NLP and machine learning directions. For example, people have done things related to make machine understand common sense. It's related to my work about adding extra knowledge to intervene in the model behavior so that we can reduce the model bias. And I'm not going to cover all of them, but I will discuss some of the connections in this talk. Okay, specifically, I will cover these papers in this talk. Yeah, and then here I say, okay, I'm done the introduction and the motivation. Next, I'm going to talk details about my work. And the first one is about the bias amplification and the calibration. Specifically, it's about these two works. Yeah. So let's start with one example on a visual semantic role labeling task. So given an image on the left, we ask the question, what's in the image? So it's clearly, it's a cooking activity, and the thing is being cooked is a vegetable, and cooking is happening in the kitchen. Now let's try to guess what's the agent in this image. As a human, the question is very easy to answer. It's a man doing the cooking thing. But with an advanced machine learning model, it said it's a woman cooking. So what's happening here? We know that machine learning and NLP models often trained on a very large data set, and those data sets usually contain biases. For example, in the task I showed last slide, the data set is actually collected from the website, and about 2/3 of images, cooking images, have women cooking. More surprisingly, when we do the analysis, we found that if we evaluate the model in a similarly distributed test set, the model predicts a more skewed result, saying about 84% of the images have women cooking. So we will call this is a bias amplification. Not only just for the cooking activity, we also do the same evaluation for multiple verbs and even nouns in a different data set. So the story is the same. The underlying corpus is biased, and after the model in the prediction, the bias is amplified. The concern that if the model used in real world, it will make different predictions for men and women in the similar context. It's not just duplicate the existing biased view of the world, but further amplifies that. And next, I will give some background about the data set and task we evaluated the bias amplification. The first data set is image city, which is the example I showed a few slides ago. So given an image of something happening, the task, the visual semantic role labeling task, produces a structured summary of the thing happening in the image. Again, like for example, this is about cooking event, and the thing being cooked is a vegetable. A central technique challenge here for this task is that some values in this image is very hard to see. Like for example, the tool used for the cooking, the spatula, is highly obscured by the hand. It have very weak visual support. In order to predict such objects, we need to introduce some structure predictor that can use the common sense that a common tool involved in cooking activity is spatula. So how will this model work? First, given the image, we pass it through a convolutional neural network to get the representations of the image. Then those representations is regressed to some potential values in a conditional random field. And then we train the model end to end by optimizing the likelihood based on the conditional random field. But again, the concern that now we have introduced this structure predictor, the model can inadvertently learn the correlation between the cooking activity and the agent being male or female. Okay, this is about the task. Next, I will talk about how to evaluate the bias or bias amplification. Sorry, I think sorry, I think I made the wrong order. So, okay, so the idea is very easy. So we will count in the training data set, we will count how many times a verb, for example, cooking, co-occurs with male or female being the agent. We then calculate the ratio of men being the agent. So in this time, the cooking activity is largely correlated with female, so we will have a small value here. And we will do the same thing. We want to know how the model performs on the unseen data set. So we will get a dev data set and train the model and do the prediction and then calculate the same ratio as we did in the training data set. And now in this dev set, we get the cooking activity with a ratio about men, like 1/3. It's more skewed than in the training data set. We call this scenario is the bias amplification. So this is how we calculate this bias amplification, and I show it in the MACQ data set. We also did the same thing, the same analysis on another task, another data set called MS-COCO. And this is a commonly used data set in the computer vision community for the object detection and image captioning. We set a multi-label classification task based on this data set, and the model used is just exactly the same as the previous one, so I will skip the details here. The task is that we want to predict if one object is in the image, as well as if a man or woman in this image. And again, we will calculate the same ratio as we did in the MACQ data set. Calculate it now, just like replace the verb as the object in the image. Now this time the snowball is more closely related to male, so we will have a larger value here. Just like by larger, I mean it's larger than 1/2. Okay, so that's the background about the data set and the task. We want to know, okay, how does the bias amplification look like in the tasks? So here is the result. Now I'm plotting the result on the two data sets simultaneously. So here the x-axis is the gender ratio in the training data set. If y-axis is the gender ratio on the dev set. So if a concept like a verb or noun is closely related to female, now on x-axis it will have small value. If the model is doing the prediction and is making exactly the same ratio as the training data set, all the dots, all the results should lie on this blue line, which is y equals to x line. Here, the yellow zone is the thing we really concern. We call it the amplified zone. So each point in this zone means that original in the training data set, the concept is biased towards one gender. And after we do the prediction, the bias is amplified. We have more skewed ratio on that concept. And we do see that many biases we previously saw have gotten significantly worse. For example, the cooking, washing, or assembling examples showing here. And we see like overall the two data set, the two tasks is showing significant bias amplification. About 70% of the concepts will have this bias amplification issue. So by far, I show that for a machine learning model, the training data set is biased. After the model, the bias is further amplified. So it comes naturally with the question, can we have a way to control those biases? So next, it comes the efforts to prevent the model from making the social biases even worse in the prediction. We try to have ways to remove the bias amplification from the model. So like I said, we want to find a way to calibrate the model prediction so that we can. Oh. Let me see. Wait, I cannot see the. I didn't see.
Someone raised it.
I just. Oh, okay. Ashma, are you asking a question? Oh, no, wait. Where is the audio? Hello. No, it's echoing. Yeah, okay. We'll just leave all the questions in the end. Yeah. Sorry for that. Okay. Okay, where am I? Yeah. Okay, I'm talking about the thing we are trying to do here is to find ways to calibrate the model so that we can reduce the bias amplification. So this calibration has been a long research direction, and people already proposed several ways for calibrating binary or multi-class cases. For example, in the binary case, if we have too many positive examples, one in the way we can calibrate the model is by putting more weights on the negative instances. But such calibration is not enough for the structured cases. Here, for all cases, we have multiple variables that are relevant to each other at the same time. And if we change one, it will affect the others in some way. And also, researchers have found that it's very challenging to do the calibration under the fairness context. So a big challenge comes for us here that how can we do a calibration with multiple variables at the same time and to maintain the model performance. Our idea is to use our original data set to calibrate and modify model predictions based on some corpus level statistics so that they are more aligned with the original training data set. Practically, we are going to do this using constraint that we formulated as the integer linear programming problem. And the advantage of this approach that we do not need to retrain the model. Furthermore, we're going to solve this ILP, integer linear programming problem, using the Lagrangian Relaxation technique. In this way, it allows us to reuse the original model inference techniques. Also, this technique is general and can be used in many other applications. For example, it has been widely used in correference resolution tasks, in dependency parsing, or information extraction tasks. But here we are the first to adopt such techniques to calibrate bias amplification in NLP. One thing we need to know here that such technique does not always guarantee we can find the optimal solution. But if we find one, the solution will be optimal, like all the constraints will be satisfied. Now, how does this ILP look like? Well, it's going to have two parts. The first part is the scoring function based on the structured output y, given the image like in our tasks. And the second part is the constraint we want to add. Here the constraint is saying for all the concepts, we want the predicted gender ratio to fall within some margin of the training gender ratio. One important thing here to remember that the predicted gender ratio is calculated by all the model outputs over the depth set. How does this work? Here is the graph, similar as the previous one. The training gender ratio on the x-axis and the y-axis is the predicted gender ratio on the depth set. Here, the dotted line is the margin, like we want the predicted gender ratio to fall within this margin for the training ratio, like the solid blue line. I plotted the dots outside the margin. In red, we call it violations, and if we satisfy our constraint, like it's fall within the margin, then it's in green. Our idea is that we want to move all the predictions in aggregate closer to this solid blue line so that we can reduce the bias amplification. Like I said, practically, we are going to solve this by Lagrangian relaxation. And this techniques allows us to wrap all the constraints to our inference procedure. It will iterate between two steps. One is to update how much the constraint is going to influence our inference. And the second step is actually performing the modified inference. Hope that we can find a solution to this program. So here we first perform the inference in our original model. So we may get the result on the left. We then use the result we have now to compute the Lagrangian multiplier. So in this case, now on the left part, we have all the agents to be predicted as female. Then we use the multipliers to update the potential values for our conditional random field model. And based on these new potential values, we do our inference again. So maybe it can change some of the predictions. If now all the predicted gender ratio are satisfied with constraint, we will stop. In reality, we will not be able to satisfy all the constraints. So we just do this for some fixed iterations and then we stop. So how does this technique work on our tasks? Here, I show the result on the image spatial data set. We see that after applying our method, all the points move towards to this solid blue line. And so the magnitude of the bias amplification is reduced. The exciting thing here that we can do this calibration at the same time with almost no loss in model accuracy. Now, after the paper is published, we further improve the results by exploring different optimization methods. We see that we can further reduce the violations to around 20%, and again, almost no loss in accuracy. So after finishing the work, we are looking for the reason why the bias is amplified. The one obvious reason is that we predict by selecting the top candidates. And this could be the key reason, but the true reasons for the amplification could be more complicated than that. So the prior analysis I showed that is only consider the top prediction. We want the model to give us a prediction, like saying the agent to be female for the cooking activity. So it's possible that the bias amplification comes from this technique. And in a following ACL paper, we wonder if we doing the analysis in a posterior distribution perspective, if the bias could be less than in the top predictions. But things will become more complicated when we consider the probability. the first question is like, how can we calculate the bias in the distribution perspective? I'll give you an example to illustrate the idea. Consider 3 images we have here to have the particular activity like cooking. For the first image, the agent to be male is predicted with probability like 0.6, to be neutral is 0.1, and to be female is 0.3, and so on for other images. And when we consider the top prediction, we need to predict the best prediction with the highest probability. In this case, we calculate the bias in the prediction is like 2/3. And then when we calculate the bias from the distribution perspective, we are going to calculate for all the 3 images, the probability of being male, like 0.6 for the first one, 0.3 for the second one, and vice versa, and divided by the probability of the agent being male or female. So you add up those probabilities here. So for the 3 images, when we calculate the bias from the distribution perspective, now it's less than 0.6. So we evaluate the bias amplification, use the distribution perspective again in the MAC2 data set we showed previously. And the left one is the result in the top prediction. And the right one is the result in the posterior distribution. So again, the x-axis is about the ratio in the training set, and the y-axis is the ratio in the prediction. The red one is the violations. So we do see that in the distribution perspective, we have less bias amplification than in the top prediction, but still we have a pretty large amount of concepts showing bias amplification. We can also mitigate this bias amplification in the distribution perspective by some techniques called posterior regularization. Intuitively, we still want the gender ratio to be similar at that in the training gender ratio, but just this time it's from the distribution perspective. And this posterior regularization is similar to the Lagrangian relaxation, is an iterative procedure. And I will skip the detail here, just like for the interest of time, but I'm happy to discuss this technique offline. So how does this posterior regularization work? We see like the left part is before adopting these techniques, we have some violations. And the right one is after we use this technique, we almost remove all the bias amplification. And I want to see one thing here, still we keep the model performance. Okay, so we finished the first part about bias amplification and calibration. Next two, I will briefly talk about our work on bias detection and bias in language representation. So like we already see this example previously, we have the cooking images, the model tends to think it's a woman cooking. But when we consider a specific case for this cooking activity, saying, okay, if we have chef hat, now how will the model make prediction? It turns out like now when we provide these chef hat attributes, the model is saying, okay, all those images about woman cooking to be male. So it's also referring to another kind of biases saying about the professional part of the cooking event. Another example I want to show that there is one paper last year during the pandemic time. They're trying to use machine learning and NLP techniques to intervene in the hiring process. They want to predict the job hopping likelihood between of the candidates. In the paper, they said, okay, it seems like their model, the likelihood are similar for male and female, meaning there is no bias learned. But is this the real case? First, like the similar likelihood between the two groups doesn't mean it's just unbiased. because they could be different in other metrics like recall or precision. And also the second part is that the likelihood is similar on the whole corpus doesn't mean it's fair everywhere. Like men can have higher hooking activity in certain occupation A and lower in occupation B, but overall they cancel with each other. So these things actually inspire us to see, can we identify the biases in local regions? Okay. I'll skip some other kind of motivative example here, just jump to the thing we want to talk here. So previously we have researchers found that in a toxicity classifier, a model is very likely to label a sentence have the word gay as toxic comments than other sentences. Therefore, the model have much higher false positive rate on the discussions about in the certain group. But we conduct a similar, we want to ask a question like, okay, will the same thing happens when we talk about the race? We found that in the same data set, the toxic detection task, when we talk about we do the toxicity detection for the race, the performance gap overall between the two groups is around 4.8. But it may be some biases there. But we see that if we randomly split the sentences to the two groups, there also is a gap between the two groups is around 2.4. So maybe you see the previous gap is not that large. But if we look at some local cluster to see, okay, when it talks about certain political topics, now the gap is suddenly becomes 19%. So it's definitely something happening here. So that's our question. So is there a way to identify such local biases? I think overall the performance seems kind of reasonable, but within some local groups, there's really some severe thing happening. This problem is actually very general and especially relevant to existing deep neural networks because those nonlinear models will have very unsmooth decision boundaries and it can behave very differently in different regions. So in this work, what we do is we want to discover the biases within some small regions and given some test data set with the ground truth. Previously, we only estimate the bias and the metrics such as the overall performance gap between different groups. Now we propose a clustering method that solves the objective function consisting of two parts. One is the original clustering loss, which is trying to group examples that are similar to each other to one group. And the second part is related to the fairness metric. They say within this group, the performance gap should be larger so that we can detect the bias. For example, in the toxicity classification task I showed the last slide, we are able to discover the some local regions with strong biases when the global bias is not that strong. So the global bias is illustrated within this red box. And the left one is just like some local groups we discovered, and especially the first two have really strong bias. When we look into these local regions and found that those highly biased regions is about certain political topics. Okay, quickly go through the last part about bias in representations. So like I said previously, the representation is very fundamental in NLP. Like almost all the NLP models are rely on those representations. And there have been a lot of work trying to improve the representation, so we have higher accuracy or F1 score in the downstream tasks. And also we have some work, people trying to understand the biases in representations, for example, in English word embeddings or contextualized word embeddings, it's including some of my work. But here I want to say one thing, that for the whole world, we have thousands of spoken languages, and English is just one of the most spoken languages. But in the NLP domain, it seems like the English is just dominate the whole research area. Like when we look at the paper published in the past few years, just like the languages being studied have really high gap. In my research, I think that NLP should go beyond the one language. So we ask ourselves a question. We would done so many bias analysis in English. How about the biases in other languages? So in this talk, I will talk this part. I will briefly talk about the biases in languages with grammatical gender. So the grammatical gender, the languages with grammatical gender, such as Spanish, they have very different behavior than English. So in English, for the nouns or adjectives, usually we just have one single token. For example, the doctor, we use doctor to represent both male and female doctors. But in Spanish, we have feminine doctor, it's called doctora, and masculine doctor, just like doctor, for different genders. And if we want to analyze bias in such languages, it's not very straightforward. Like you cannot directly adopt the techniques you use in English to those languages because of this kind of a more complex grammatical gender. So in my research, in one of my research, we studied the bias in multilingual embedding. Is beyond the English language itself. For multilingual embedding, we know like it's widely used in cross-lingual transfer learning. Basically saying, if you train a model in one language, you can transfer that language to other you can transfer that model to other languages. And to obtain such multilingual embeddings, one common way that you train monolingual embeddings separately, and then you align all of them to one shared space. As I said, there are different language properties for the languages spoken in the world. So in this work, we want to understand the biases in the multilingual embeddings from the three perspectives. One is the impact of the language property. And also when we get the multilingual word embeddings, we have the target align space. Will this affect the biases? And also how will the bias in the embedding affect the cross-lingual transfer learning? High-level idea that all the languages we analyzed, the English, Spanish, German, and French, they all have biases. And when we align the languages to different target space, the bias behavior will be very different. For example, if we align all of them to English space, all the bias in those languages will increase. And if we align them to Spanish, the biases will decrease. We think it's related to the grammatical system in the different languages. And also all the biases in those multilingual embeddings will influence the downstream tasks in the cross-lingual transfer downstream tasks. So we do see here when we transfer the model from English to Spanish or vice versa, there will also be bias. There, biases commonly exist. Okay, maybe I just stop here. So in this talk, I particularly talk about three directions I did from the representations, how to discover the bias, and also about the bias amplification and calibration. This work lies the background to envision my future directions to continue building accountable NLP models. For the future direction, the first thing I think about is that how can we teach our model to understand and follow our instructions? For example, like I said, humans also have their own bias, but they can learn something and change their perceptions. And can we do the same thing to our model? So some challenge here is that the instructions can come in various formats. For example, in some natural languages, I told the language, you cannot do this. And also it can come in a more, for example, a more model understandable way, like it's not in natural language, but for example, in some embedding format, etc. And also the instructions, they can come in advance. I provide all the instructions at first, and then teach the model, or it comes at real time. So how the model can deal with those different variations of instructions can be challenging. The second direction I want to do is how to understand the model behavior. Now, nowadays, models usually make just make the final predictions, and that could make the user ask why this happens. I don't want to believe you. But if we can do the prediction and at the same time say, okay, your request is not approved because of reason A and reason B, now maybe it's more accessible. But if when we read the explanations for the models, it said because I don't like your zip code, so your request is not accepted. That definitely means something is wrong with the model, so we can go back and fix the model. So this line over can do the early bias detection and provide some information for us to fix our existing model. In the long term, I strongly believe that advanced NLP or machine learning techniques can play a significant role in our daily life in the real world. A significant case is that we can adopt those models to benefit social good. That could require an interdisciplinary research across computer vision, NLP, or maybe biomedical domain or psychology domains. In the future, I would like to explore more on this interdisciplinary research for social good applications. Okay, here just like some other activities I did during my PhD life, and I will just stop here and to take questions. And also thank you for your attention.
We don't know how to do that.
Yeah, I think if I turn on this.
Maybe let's turn off the mic. Okay. So does anyone has a questions in the Zoom or people here? Yeah, so for people in the Zoom, you can type your question in the chat, or you can raise your hand and then we can unmute you. Yeah.
the future. Right. Yeah.
You should repeat the question.
Oh, yeah. So the question is like, what the projects I want to do in the future? I rephrased that a little bit. Yeah. So some like the future direction I showed in this, like in the last section of the slides. And also something I want to do is about the general robustness. Like I think like the social biases is also related to model robustness, and other than the biases, for example, related to gender or race or ethnicity, those things, we also have seen that a lot of research saying, okay, there are some data artifacts in our training data, and how can we deal with those things is also very challenging, and people are trying to do things related to that direction. And I'm interested in those things. And also one way, also part of the future direction I said a little bit is like about the model interpretation, like why the model is making such predictions. Can we dig out what's wrong in the prediction part so that we can have better ways to control the prediction and make the bias less bias in our model? Yeah. There's something, yeah, in my mind, but I believe there are also a lot of other interesting directions. For example, in multimodal kind of systems, how can we leverage the information from different modules to help our final predictions? That's also very interesting. Yeah.
Yes, you will have questions.
Okay.
So do you think it's possible to actually remove all the bias from the model?
Okay, the question is like, do I think it's possible to remove all the bias in the model? For me, I think for now, I think it's not. I would say it's not possible. I just say it's very challenging. So we actually have one project trying to see, okay, if we know the data set is biased, and we want to see, okay, if we make the data set balanced regarding to gender, how the model performs regarding to the bias amplification. And we do found that it doesn't help a lot. It's still showing some bias amplification. So we go back to see what's happening. It turns out like even though you make the gender ratio balanced, but for example, in the image, the background related to different genders can still be very different. For example, females in the images may be more correlated with some pink umbrella, and the male more related to blue umbrella. And those implicit correlations are really difficult to disentangle and to balance. And also it's very hard to remove them from the model. So those implicit correlations, for now, it's very difficult to address. So, but I guess like again, very many researchers are working on these directions. Like let's just keep the hope and work on these directions. Yeah. I hope that answer satisfies. Yeah.
Is there any more questions?
Oh, there's one question from the Zoom. How much work is being done to be inclusive of other gender identities than the standard male or female in the bias detection and mitigation tasks? Okay, very good question. So I think at least one of our group members is working on this direction, like with the postdoc students in our group. So they trying to first understand the harm, like from very kind of, I'm not saying the non-standard, but like from other gender indications, they're trying to understand existing models harms on those identities. And I would say this is a developing direction. And most of our existing work, including some of mine, is doing research on the just like binary genders. But I think like researchers now have realized this problem, and they are putting efforts on this direction. And also the group members at our lab is organizing the workshop on this direction to raise the awareness of this direction. Yeah, thank you for your question, Jacob.
So, okay, then, so thank you everyone for attending this talk.